In this video, I will talk about time derivatives in a rotating frame of reference. With blue here, I'm showing my inertial frame of reference S sub 0. This is the origin, and I have the x naught direction, the y naught, and the z naught direction. This is my inertial frame of reference. And with red, I show a rotating frame of reference. These are the three axes, x, y, and z, and this frame of reference, the red one, it is rotating. Now, this weird symbol that you see here, this is actually the uppercase omega. So one way to write an uppercase omega is this, the circle and the line, and because this is the angular velocity vector of the rotating frame of reference, I'm also doing one more line on the top to show that this is a vector. Okay, the lowercase omega looks like this, if that's a vector. Anyway, so this is what that represents. Now, let's say I have a vector q, whatever that is. Let's say this can be a position vector. So let's draw. If I draw, if this is my vector q, okay, this is q. I'm not going to specify if it's position, velocity, or something else. It's just a vector at this point. I can take the time derivative of this vector q with respect to the rotating frame of reference and with respect to the inertial frame of reference. Okay, it is a vector. Now, let's say that I write the vector q using its components in the rotating frame of reference. So I'm gonna say qx x hat plus qy y hat plus qz z hat. Now let's say, okay, so I've written the vector q in terms of its components in the rotating frame of reference. Now, if I take the time derivative of this vector in the rotating frame of reference, then I need to take the time derivative of all of these. Okay. For the rotating frame of reference, x hat and y hat and z hat are all constants, because those are the unit vectors of the rotating frame of reference. So really, I just need to do dqx dt times x hat plus dqy dt y hat plus dqz dt z hat. Now, here's the thing. If I want to take the time derivative of q with respect to time, but in the inertial frame of reference, let me show you. I'm going to show you the following. So this is x, and this is my x hat unit vector. If you are in the rotating frame of reference, x hat always points in the same direction. Okay, even though your rotating frame of reference is rotating, it is spinning, you are spinning with it, so x hat stays constant. But if on the other hand, if you are the observer, you're here, you are using your inertial frame of reference, and you're looking at x hat, the unit vector of the rotating frame of reference, then as your x-axis is rotating, then of course the unit vector x hat will also rotate, right? For the observer on the inertial frame of reference, since the x-axis is rotating, of course the x hat unit vector associated with this axis will also be rotating. This means that when I take the time derivative, I need to do dqx dt x hat plus, and this is important now, the x component of q times dx hat over dt, and this derivative will be taken with respect to the inertial frame of reference. And then I have to do the same for the rest. dqy dt y hat plus qy dy hat dt, and this derivative will be from the inertial frame of reference, and the same thing. So this will be dqz dt z hat plus qz dz hat dt in the inertial frame of reference. Now, this term and this term and this term, they are you see that we got those before as well, but these terms need to be included when you find this time derivative from the inertial frame of reference. Now, well, how do I calculate something like this? Okay, I can help you. If you remember, we talked about before V equals omega cross R. What is V? V is just the time derivative of R. So dr dt equals omega cross R. You can replace R with anything you want. So, for example, you got a different vector, whatever you want to call it, dA dt omega cross A. Okay. Now in this case, I have dx hat over dt, so this is going to be simply omega cross x hat. Okay. So I'm going to keep let's do the following. dq, okay, so I'm gonna bring some terms together. dqx dt x hat plus the same thing in the y dt y hat plus dqz dt z hat, okay, plus the rest. Now all of these is what I got when I did the time derivative with respect from the rotating frame of reference. So I can say this is equal to dq dt from the accelerating frame of reference, since that's what I got. Now I also have the rest, and this is going to give me qx dx hat over dt is going to be omega. Well, actually, it's the uppercase omega. Omega cross x hat plus qy, the angular velocity of the rotating frame of reference, cross product with y hat, plus qz omega cross z hat. Now, another way to write this is omega cross q. Okay, and I forgot these are vectors. So q, I forgot q is a vector. So okay, that's it. So this is, okay, this expression this is how you can take a time derivative of a vector in an inertial frame of reference. This is how you can connect the time derivatives in the two frames of reference.